Hello everybody, welcome to the last lesson that we're going to do. There's one more lecture that comes after this, and that's on the beauty of physics, which is Philosophy Fridays, and what we've learned all year put together. But for now, this lecture is going to be on waves. It's going to be a lot of vocabulary, not a lot of calculations. Mainly vocabulary that you're going to need to know when it comes to the Unit 4 assessment, which is coming up soon. So here we go. Waves and light. That's the main topic. So first of all, you need to know what the different parts of the wave. So the wavelength is defined as the distance from one crest to the next, right? And the crest is the top, the trough is the bottom, and then the amplitude is how far the crest is from the equilibrium, from the zero, right? It's not how tall the wave is from crest to trough, but only from crest to middle, you could say. All right, and so the wavelength, again, is the distance from one crest to the next, and then the amplitude is the height of the wave above the axis. Okay, now if we're looking at a different kind of graph, this graph is a displacement versus time graph. The other one was displacement versus position graph. The distance, or the time from one crest to the next, is a period. So a period is the time it takes for one full cycle. We saw that when we talked about circular motion earlier. A period is the time for one full cycle. If you keep that in mind, that'll help, period. One full cycle. That applies to circular motion, that applies to wave motion. Okay, and then the frequency is how many crests pass each second. So it's actually the inverse of the period. Take the period and then flip it 1 over, and that gives you the frequency. And you can tell by the units for frequency is hertz. And hertz are 1 cycle per second. All right, now here are some very simple calculations. The way that you calculate waves is, the wave speed is wavelength times frequency. That thing that looks kind of like an H is actually the lowercase Greek letter lambda. So V equals lambda F. That's V equals wavelength times frequency. Okay, or V is also equal to wavelength divided by period. That also works. Okay. So here's an example. A human voice can have a frequency of 80 hertz and a wavelength of 4.3 meters. What is the speed of sound in air? Well, we use our calculations. V equals lambda F. So lambda is the wavelength, and that's 4.3 meters. And the frequency is 80 hertz. So the speed of sound in air is about 344 meters per second. The speed of sound is different in different media. The speed of sound is different in water. It's different in solids. Right? If you tap one end of a pipe, that someone who's listening to the other end of the pipe, they'll hear it come through the metal of the pipe before they'll hear it come through the air of the pipe. Sound actually travels much faster in water and in solid than it does in air. So here's an example about light. Now light is different because light is an electromagnetic wave. It doesn't need air or water or a solid to pass through. We're going to get to that distinction later. Anyway, blue light has a frequency of 625 times 10 to the 12th hertz. Okay, that means that it vibrates 625 times 10 to the 12th times each second. So it's vibrating a lot. And it has a wavelength of 4.8 times 10 to the negative 7th meters. Right, so it's point and then 6 zeros, 48 meters. So it's a super tiny wavelength that blue light has. And I'm asking, what's the speed of light? So again, lambda F, but here it gets a little messy with all the scientific notation. 4.8 times 10 to the negative 7th is the wavelength. And then the frequency is 6.25 times 10 to the 12th hertz. You multiply those together, you get about 3 times 10 to the 8th meters per second. That's 300 million meters per second. That's how fast light travels. Okay, middle C on a piano has a wavelength of 1.3 meters when the speed of sound is 344. So what is the frequency of middle C? Right, so now I'm asking for something different. You have to rearrange the equation. If V equals lambda F, then F equals V over lambda. Right, you take both sides, divide by lambda. You end up with 344 meters per second divided by 1.3 meters. It gives you 262 hertz. So middle C has a frequency of 262 hertz. That means 600 or 262 vibrations per second. Okay. Now the speed of sound is 344 meters per second. The speed of light is 300 million meters per second. So why do you see lightning before you hear it? Right. It's really simple, because light is so much faster than sound. Sometimes people ask, is light faster than sound? And the answer is a resounding yes. It's much, much, much faster than sound, right? Almost 1,000,000 times faster than sound. And so that's why you see the lightning. When you see lightning, you see it almost instantaneously as soon as it happens. But it takes a while for the sound to get to you. All right. And so this is something that people will talk about. They'll say, oh, when you see lightning, you count, and then however many seconds it is, that's how far away it is in miles. Right? But that's not true. So we can use science and what we know about sound and the speed of sound to figure this out. If you count the number of seconds, then you can figure out how far away it is, but we got to figure out the rule first. The speed of sound in air is 344 meters per second. How far does sound travel in miles in 1 second? And how long does it take sound to travel 1 mile? All right, so now we're converting to miles, something that we understand, so it's a little bit easier. And we're asking, how far does sound travel in 1 second in miles? Okay, and here's the calculation. V equals delta x over t. This is from way, way back in September we came up with this equation, that speed is distance divided by time. So the distance is velocity times time, 344 meters per second. So it goes 344 meters in 1 second. And then we convert that to miles, and we get 0.2 miles. That's about 1/5 of a mile. So if you see lightning and then you hear it 1 second later, that means it's only 1/5 of a mile away. It's pretty close. And then how long does it take light to travel 1 mile? About 5 seconds. All right, so if you count to 5 and then you hear the thunder, then you know that the lightning was about a mile away. Now, one question came about: what happens when you travel faster than the speed of sound? And some people, they didn't know. They thought that maybe when you traveled faster, you tried to break the sound barrier, the airplane, because that's what they were using at the time to try to figure this out. Maybe the airplane would just break apart into pieces. And there's a great movie about that called The Right Stuff. At the beginning of the movie, it's about the man who broke the sound barrier, and I recommend that movie. Traveling at the speed of sound is called Mach 1. If someone travels twice the speed of sound, that's called Mach 2. Right? But what happens is they end up with this shock wave. And you see this even in a boat. For example, if a boat is traveling faster than the waves it produces in the water, it ends up with this shock wave behind it. And so when you see an airplane breaking the sound barrier, there's this shock wave that it produces, and you get condensation in the air, and it looks like a little cloud. Okay, so now we're going to talk about wave types and wave interactions. First of all, there are 2 types of waves. Really what a wave is, it's some medium, it's something that's oscillating back and forth. Right? So there are longitudinal waves and there are transverse waves.
In a longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves. In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
All right. A transverse wave is when the the wave is traveling, say, side to side, but the medium itself is going up and down. And then a longitudinal wave is where the particles are vibrating in the direction that the wave is traveling. All right. Sound is an example of a longitudinal wave. The sound goes outward and it's pushing the it's vibrating the air particles back and forth. And here's an important thing to know. All waves carry energy. Right. So what about waves? Well, water is a combination, like waves that you see in the ocean. Water is a combination of waves. It's actually longitudinal and transverse. If you were to pick a water particle and watch it, it would actually kind of be going in a circle. And then we have mechanical waves and electromagnetic waves. So a mechanical wave requires a, uh, a medium of some kind. So it needs air or a liquid or a solid. Examples are sound waves, slinky waves, pressure waves, earthquake waves. Earthquake waves, they go through the surface of the earth, right, and even through the middle of the earth. And it's using the solid earth as a medium for the wave. Water waves, another example. If you don't have water, you can't have water waves. Sound, you need some type of medium. That's why they say, the tagline, I think, for the movie Alien was, "In space, no one can hear you scream." And that's not entirely true, because we use radio, and they could hear over the radio someone screaming. But if you didn't have a radio, sound doesn't travel in space because there's no air. There's no medium through which the sound can travel. And that's an example of bad movie physics. Oftentimes, when you're watching something like Star Wars or Star Trek, or even some of the Marvel movies, the Guardians of the Galaxy, when there's an explosion, you hear it, right? You see some spaceship or some planet or Death Star exploding, and you hear the explosion. There would be no sound as something explodes in space. You would see it, but you wouldn't hear the explosion. But that would also not be really exciting. So they put the sound in there for the movie. Electromagnetic waves. These are light waves. And we've got everything from, X-rays to radio waves to microwave. It is a type of light. We call a microwave because it uses microwaves, that type of light, to heat up the food. Visible light, all these things. And this doesn't need a medium. It can travel through the vacuum of space, and it's a good thing, because if it didn't travel through the vacuum of space, the heat from the sun wouldn't get to us. The heat from the sun gets to us through electromagnetic waves. And so it's a good thing it is the way it is. And we can also see the stars, which are hundreds of light years away, because the light travels that far through the vacuum of space. And here's a funny little meme I saw once. Imagine seeing noises. That's probably what you would look like if you put Red Bull in your coffee. All right, so 2 types of waves, longitudinal versus transverse, and also 2 types of waves, mechanical, in other words, something that needs a medium, some material to travel through, and electromagnetic waves, 2 different types of waves, 2 ways of distinguishing different types of waves. And then there are interactions, wave interactions. Waves reflect off of different things. So we call that reflection, when the wave is traveling and it hits something and then reflects back, bounces off of surfaces. Reflection is one way that some animals figure out where their food is. Dolphins and bats, for example, they use reflection. They make a sound, and then they hear when it comes back to them, and they know where the food is. Blue whales, some whales, they make a sound, and they know where the shore is because they hear the sound bouncing off. All right, and they're very, very, very loud. Bats and whales are extremely loud, but we're not up all night from the bats, because we can't hear the frequency where they emit their sounds. It's so high pitched we can't hear it. Right? Another interesting piece of technology is ultrasound. This is my son Paxton, 5 months before he was born. That's the back of his head there, and you can see his body, his ear even. All right. Ultrasound is bouncing sound waves through the body and then picking up those sound waves as they bounce back off of the different surfaces. Amazing, very cool, and always very fun to see an ultrasound of a child for the first time. Okay, another type of interaction is refraction. When a wave enters into a new medium, so it goes into water, light goes into water or something, then the wave will actually bend. And that's called refraction. This is how lenses work. Light hits the lens and it bends. And if you manipulate the lens, you can change the light and how it bends so that it focuses in a different place. And that helps us to see. So here's an example of refraction, the light going through the water. 2 glasses, same setup. One has water in it, one has a different liquid in it, because different liquids have different ways that they refract light. Right? Diffraction. Diffraction is when waves pass around a corner and then spread out. So here there are waves going, hitting this wall, and then there's a little hole, and then the waves are going through that hole and kind of radiating out from that hole and bending around a corner. Another type of interaction is polarization. This only works for transverse waves, and that's when you have, for example, light coming in at all different angles, going up and down, side to side, all this stuff. But it goes through some, kind of like a fence, a filter, and then only one orientation of light makes it through. That's called polarization. Some people wear polarized lenses because a polarized lens can polarize out light that is bouncing off of surfaces, and you get a glare, like on water or when you're driving. Fishermen and drivers oftentimes will wear polarized lenses. It'll take the glare off the water. They can actually see into the water, helps them see the fish. And then drivers, sometimes it takes the glare off of the cars that are going around near them. All right, and then interference. Waves can pass through each other, and when the crests are lined up, you get constructive interference. The waves actually get bigger. And then destructive interference is when you have the crest and the trough lined up, and then they cancel each other out. And then when you have two waves that are very similar in frequency but not quite the same, then you get beats occurring. Some of you who play instruments are familiar with this. When you're tuning and you're getting close to what you're trying to tune to, you hear this kind of like wah 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 sound. That's the beats. You're getting constructive and destructive interference. And then once you hit right on, you don't hear that anymore. And resonance. An example of resonance is that if you have someone on a swing, a kid on a swing, and you push them at the right frequency, they actually go higher. But if you were to push them at random frequencies, just kind of at random times, they'd stop, they'd start, they'd stop, they'd start. That's because there's a natural frequency that the swing is going to go. If you match that frequency, then you get resonance occurring. The same is true for anything. If you take a vase or something, like a glass, and you hit it, it makes a sound. If you were to vibrate that thing at that frequency, it would resonate inside of the glass, and it could break. And this is what happens when they lick their finger and they pass their finger around the top of a wine glass. You get resonance occurring. It's pretty cool. Phenomenon. So different wave interactions. Again, just vocabulary here. Reflection, refraction, diffraction, polarization, and then different types of you get interference, and different results of interference are constructive and destructive. You get beats and resonance. Right? And then from the beats and the resonance and the interactions, constructive and destructive interference, you get standing waves, and then we also have something called the Doppler effect. All right, so a standing wave is created when the length of a string corresponds to a multiple of half the wavelength of a wave. The waves being created and the waves reflecting interfere and create a standing wave. And this is resonance, right? So when we get resonance, we get a standing wave occurring. Most common example of this is jump rope. So you have a wave, the rope is going around, and they are pulsing it at exactly the right rate to make it go around. And so that is a standing wave, and it's a standing wave of half a wavelength, right? Think of when it's up in the air, if it were to go down and up again, that would be the full wavelength, but it's only half a wavelength. So that's an example of a standing wave, and that's resonance. So here's an example of a standing wave. This is a 3 antinode standing wave. And you can see there are actually 3 half wavelengths here. There's one full wave and then another half wavelength in this example. And here's the formula. The top one is kind of like what you have when you're doing jump rope, and there the length of the string is lambda over 2. It's the wavelength divided by 2. But if the length of the string is equal to the wavelength, then you get 2 antinodes in the standing wave. And what happens is the middle doesn't look like it's moving. If the length of the string is 3 halves of the wavelength, then you get 3 antinodes. Right? So what we're looking at here is multiples of half the wavelength. 1 times half the wavelength, 2 times half the wavelength, or 3 times half the wavelength.
So what we have here is a frequency generator. It's connected to what's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. He sends a wave down to this end, the wave reflects, comes back. Now, if I set it to just any old frequency, they're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that come down and reflect, destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera. So here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice, this is a node, this is a node, and the middle's a node. So we have 3 nodes for this wave. Now, like I said, second harmonic, well, what's the first one? The first one will be half this number, so 8.5. And there we go. It's basically the scenario of a jump. Now, I can find all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5, I guess that was around 25.5. And there we go. So that's the third harmonic. How many wavelengths is this? Well, it's 1.5. Yourself that it is 1.5 wavelengths. Well, let's go to the 6th harmonic. Beautiful. And it's 6 times the fundamental frequency, which we measured in the beginning.
Then we have the Doppler effect. The Doppler effect is when an object is moving towards you, but it's emitting a sound. And it actually changes the frequency because it's giving off at one frequency, but those waves are hitting you sooner than they're being given off because the object is moving towards you. Right? And so it kind of compresses that wave as it's moving towards you. And then when it's moving away from you, the sound gets lower in frequency because it's moving away. So it's like it stretches out the wave. This is an example of this is in maybe an old movie when an airplane flies overhead. It goes, right? High frequency to low frequency. Why? Because it's moving towards the person, the camera, and then it's moving away from the camera. The person in the plane isn't hearing, he's hearing a steady hum, not the change in frequency. But the person on the ground who's being flown over does hear that change in frequency. And that's because of the Doppler effect. And it's the Doppler effect in astronomy that helps us know how old the universe is, because the universe is expanding. How do we know the universe is expanding? Because we look at light from distant stars and different distant galaxies and other things happening in those galaxies like supernovae, stars exploding. And the scientists know the different frequencies of light, and they see that that light is stretched out. It's been redshifted. So from that redshift, they can tell how fast those galaxies are moving away from us. And that's so this Doppler effect also happens in light, and that's how we know that the universe is expanding. Also in black holes, I mentioned this in the lecture on the physics of the movie Interstellar, but light, as it's going out of a black hole, gets redshifted, right? It gets stretched because the space-time itself is kind of stretching out. And so what is 1 meter at one place is more than 1 meter in a different place as you get further out from the black hole. And the light wave eventually just gets redshifted down to 0 energy. Higher frequency is higher energy light. For example, X-rays, high frequency, high energy, right? Enough energy to knock around molecules in your DNA and maybe create cancer or something like that. Okay, so that's it for your last lesson. We're going to wrap up here soon. Hang in there. You're almost done.